question today is, what are some examples of types of forces? First, what we have to understand is what a force is. And a force is a push or a pull acting on an object. We measure force in the unit of newtons if we're in the metric system. Now, weight, we're going to learn today that weight is a type of force. So in the metric system, the unit of weight or force will be in newtons. In the English system, here in the United States, we use the unit of pounds. You're probably familiar with this when you weigh yourself on a scale. Remember that weight is a type of force. We're going to learn that, I should say, later on. And so therefore, force of any kind is going to be measured in pounds in the English system. We're going to focus in our studies on newtons instead of pounds. Now, force is a type of vector. And a vector we usually represent with an arrow. And that arrow represents the magnitude of the vector, which means the size. And it also shows us the direction of the vector as well. So therefore, a vector quantity has both magnitude and direction. We've learned about a few different types of vectors already. What I'd like you to do is pause the video here and see if you can't write down the different types of vectors that we've already learned about. In addition to force, which is one, there are 3 other types of vectors that we've learned about. So pause the video and see if you can't write down all the vectors we learned about. Okay, welcome back. The types of vectors that we learned about here in this class are force, that's the new one we're learning about. We also learned about acceleration, velocity, and displacement. All those quantities have both magnitude, or size, and a direction. Now, the opposite of a vector is a scalar. And a scalar quantity has only magnitude. There is no direction involved with a scalar quantity. We've learned about 3 different types of scalars this year. What I'd like you to do is pause the video and see if you can write down all 3 scalars that we've learned about. All right, well, welcome back. The examples of the scalars that we've already learned are mass, speed, and distance. None of those things have any kind of direction. Now, a lot of times when we draw objects, we'll draw things called free body diagrams, and on this diagram, we draw all the forces acting on the object. And we draw them with arrows representing the forces. Anything that touches the object is going to exert a force. In addition, anything that touches the object, gravity also exerts forces as well. So what I'd like you to do, we're going to draw the upward and downward vectors, the upward and downward forces, acting on this scaffolding. This is a beam here that painters and a lot of times window washers might use in order to wash the windows way up high or paint at very high heights. So pause the video, see if you can't draw the different forces acting on that scaffolding, acting on that beam. Okay, there's actually 5 different forces that are acting on the beam. Anything that touches the beam exerts a force on it. So we have the tension of these 2 strings, these ropes. They touch the beam, and so they exert an upward force holding up the beam, holding up the scaffolding. There's also 3 objects on the beam. All 3 of those exert forces as well, and they are exerted by gravity, which pulls down. Now the bucket's very small, so it has a small vector, a small force acting on it, so we draw a very small arrow. And then the person, the second person, also exerts a force downward from his gravity as well. There's actually one other force acting on this beam, and it is the gravity of the beam or the scaffolding itself. Whenever we draw the gravitational force of the object itself, we always draw it from the middle. So in total then, there's the 5 things touching the scaffolding, and then the gravitational force of the scaffolding itself, which makes 6 forces total. Now, the force that we're going to focus on today is the gravitational force, also known as the weight. And unfortunately, a lot of people use the terms mass and weight interchangeably, but they are very different. Mass is considered to be how much matter an object has. Now, what is matter? Matter is anything that takes up space and has mass. So if we think of it this way, matter is really just the thing that the object is made up of. And all things are made up of, all objects are made up of atoms. So really the mass is describing how many and what types of atoms an object has. So again, mass is really describing how many and what types of atoms an object has. Weight, on the other hand, is a force, and a force is a push or a pull. In this case, it is the pull from gravity, from the planet that you're standing on, or perhaps it is a moon that you're standing on. Another name for weight is gravitational force, since it is the force or pull of gravity. Now, what I'd like you to do is answer these two questions, see if you can answer them first, and then check to see if you are correct later. But the first question is, does a person's mass change if they are in outer space? So what I'd like you to do is, in your notes, write down an answer and see if you know, does a person's mass change if they are in outer space? Also, I want you to see if you can answer, does a person's weight change if they are in outer space? So I would like you to answer those two questions, pause the video, answer those two questions, and once you're done answering them, unpause the video and see if you're correct. Okay, welcome back. So does a person's mass change if they're in outer space? And the answer is no, the mass does not change. If I go into outer space, remember, mass is really telling us what number and type of atoms that we have in our body. So if I go into outer space, I still have the same types of atoms, and I still have the same number of atoms. So my mass does not change. However, does a person's weight change if they are in outer space? And the answer is yes, the weight will change. So the weight will change because if you go in outer space, there's less gravitational pull on you. So because gravity pulls less, there is less weight in outer space. If you go to a place like the moon only has 1/6 the gravity of what we have here on Earth. So if I weigh, let's say, 180 pounds on the Earth, and I go to the moon, I'll only weigh 1/6 of that, or 30 pounds. It's a great weight loss program. Go to the moon, you only weigh 30 pounds. However, you still have the same number of types of atoms, so you still look the same. In other words, your mass has not changed. Now, there is a relationship between mass and gravitational force. And that relationship is shown here in this circle equation. In this circle equation, F is the force. We put a little subscript of G to show gravitational force. So F sub G is the gravitational force, also known as the weight, measured in newtons. N represents the mass. And we measure mass in kilograms. And then finally, G is the gravitational acceleration. And on Earth, the gravitational acceleration is 9.8 meters per second squared. That number will be different based on what moon or planet you might be on. If you go to the moon, again, it's 1/6 of that, or 1.6 meters per second squared. This then shows us that to calculate the gravitational force, we are going to multiply the mass and the gravitational acceleration. So the formula for gravitational force, because they're side by side, is mass times gravitational acceleration. If instead I wanted to calculate the mass, then I'm going to take the gravitational force and divide by the gravitational acceleration. So depending on what you want to solve for, either multiply or divide, the circle equation will help you do so.